All right, AP Stat kiddos. This is binomial distributions, section 8.1, part 1. You guys need to get out your paper for notes. You also will need your calculator, and you should have done activity 8A for homework, so get that out as well. Feel free to pause this video anytime you need to, because I probably won't pause long enough for you to get all the notes down. So, binomial distribution, section 8.1, part 1. All right, look at your activity 8A and grade your own, okay? Here are the answers. All right, so pause again if you need to. Many random variables seen in practice amount to counting the number of successes in n independent observations, such as the number of questions you answered correctly out of the 10 multiple choice questions you guessed on in activity 8A, or the number of doubles in 4 rolls of a pair of dice, or the number of defective items in a random sample of 20 items. The binomial distributions are an important class of discrete probability distributions. If you're presented with a random phenomenon, it is important to be able to recognize whether it's binomial or geometric, which we'll work on in section 8.2. So to determine if something is actually a binomial situation or in a binomial setting, then I want you to check BINS, B-I-N-S, BINS. If it is indeed a binomial random variable, then it is binary. Each trial has only 2 outcomes, a success or a failure. Binary. The I is for independent. All trials are independent. That is, knowing the result of one trial tells you nothing about the result of any other trial. N, there is a fixed number of trials, N. A fixed number of trials, N. That's important because that distinguishes binomial from geometric, which we'll work on in section 8.2. And S, the probability of a success, which is called P, is the same for each trial. The probability of a success, P, is the same for each trial. So if a situation is indeed binomial, then all of these BINS will check. And if they're asking us whether or not a situation is binomial, then we would have to state all of these to prove something is binomial. So again, B for binary, there's only 2 outcomes, a success or failure. I is for independent trials. All the trials are independent. Knowing what happens in one does not affect what happens in the next one, or knowing something about the first doesn't tell you what's going to happen in the next. And there's a fixed number of trials. And S, the probability of a success is the same for each trial. All right, so if data are produced in a binomial setting, then the random variable X, the number of successes, is called a binomial random variable. And the probability distribution of X then is a binomial distribution. So tell me whether this is binomial or not and explain. The pool of potential jurors for a murder case contains 100 people chosen at random from the adult residents of a large city. Each person in the pool is asked whether he or she opposes the death penalty, and X is the number who say yes. All right, so what do we need to check to determine whether this is binomial or not? Yeah, we need to check BINS. So let's go through. B, binary. If X is the number of people who say yes, then assuming that they can't say, I don't know, they have to answer yes or no, then yes, this is a binary outcome. They either say yes or they don't say yes. They say no, or we could consider they say yes or they say something other than yes, I suppose. So either way, this is binary. Because there are 2 outcomes, yes or not yes, let's say. I for independence. So whether one person says yes or not yes should not affect the next person. Knowing whether the first person says yes or not yes should have no impact on the second person. If this is truly a large city and we're taking 100 people at random, then the responses should be independent. Obviously, if you ask people all from the same family, then their responses may not be independent. But if this is truly a random sample from a large city, then we can consider the responses independent. And I'm going to say independent observations, or independent trials, I guess I should say, because this is an SRS from residents of a large city. N, is there a fixed number of trials? Yes, there were 100 people chosen at random, and they're going to ask every person whether they say yes, they oppose the death penalty, or other than yes. So, yes, there are 100 trials. Not trails, trials. And what about the S? Assuming that, it's a 50-50 chance that they say yes or something other than yes, then yes, we can assume the probability is the same. Obviously, again, if this is from some small community or some family, then the probability of saying yes or not yes may not be equal, but let's assume that it is a 50-50 chance here. So, yes, the probability of success, which is yes, is the same for each trial. So, yes, this is a binomial situation. All right, how about this? For number 2, at peak periods, 15% of attempted logins to an email service fail. Login attempts are independent and each has the same probability of failing. Darcy attempts to log in repeatedly until she succeeds. X is the number of login attempts it took to get through. So again, is this a binomial situation? Yes or no? So if we go through and check, our B is yes. She either fails or doesn't fail. I tried to type succeeds, but she either fails, which is a success. No, that's not true. Sorry, I need to read the question again. X is the number of login attempts it took to get through. So she either logs in or doesn't. For I, it's stated that the attempts are independent. For the N, is there a fixed number of trials? No. It says X is the number of login attempts it took to get through. There is not a fixed number. She's not trying 25 times and counting the number of times out of 25 she logged in. She's just counting until she succeeds. That's the difference between a binomial and a geometric, which we will talk about in section 8.2. So no, there is not a fixed number of trials. S, it is stated that the probability of success is the same. So this is not a binomial situation. All right, so the binomial distributions are important in statistics when we wish to make inferences about the proportion P of successes in a population. A typical example, an engineer chooses an SRS of 10 switches from a shipment of 10,000 switches. Suppose that, unknown to the engineer, 10% of all the switches are bad. So the engineer counts X, the number of bad switches in the sample. Again, to make some guess as to what the population proportion, the parameter of all bad switches is. So the last example shows how we can use the binomial distributions in the statistical setting of selecting an SRS. When the population size is much, much larger than the sample, then a count of successes in an SRS of size n has approximately the binomial distribution. So the binomial probability that you get exactly x equals k successes in n trials is given by this formula, P probability of x equals k, like x equals 2 successes or x equals 50 successes or whatever, is equal to n choose k, we'll talk about this in just a second, n combinations taking k at a time, or yeah, that's how, yes, that's the right way to say it, times the probability to the k power times the complement, 1 minus the probability, to the n minus k power. Okay, and that n choose k coefficient there is the binomial coefficient. N choose k, this is another way to write it, n choose k, combinations instead of permutations. This is equal to n factorial over k factorial times n minus k factorial. And I think we've talked about the factorials a little bit, but you don't actually need the factorials, and you actually don't even need the binomial coefficient, but if you wanted to, it's in your math and then over to PRB or PROB, the factorial button's there, but then you can use number 3 for NCR, but we're not even going to use either one of those because we're going to use our calculator to do the binomial probability. But before I show you that, I want to remember to tell you that this formula is on the formula sheet. That is on, okay, this is going to be hard for me to write like this. Sorry, I'm trying to write with my finger on the, I'm going to say just FS because it's hard for me to write with my hand. Okay, on the formula sheet. That formula is on the formula sheet. But you don't, well, I was going to say you don't really need the formula because it's in your calculator, but you do need the formula to show your work. But then you don't actually need to calculate it with the formula. You can use your calculator to do the calculation, but you do need this formula to show your work on the AP test. That is important. Okay, so in your calculator, to calculate that binomial probability then, you can go into your second vars And then I can't tell you which letter or number it is because it depends on your calculator. In mine, if I go to second vars, and then it's quicker to scroll up. My binomial PDF is A, but in my TI-83 calculator, it's 0. So I didn't know what letter or number to put there. So you find it in yours. Binomial PDF, N, P, X, where N is the number of observations, P is the probability of success, and X is the value that you want for your random variable. Okay, so let's try one. Number 3, each child born to a particular set of parents has a probability of 0.1 of having blood type O. If these parents have 5 children, what is the probability that exactly 2 of them have type O blood? So I think it may be easier for me if I pull up, if it will let me pull up my equation editor here so that I can put in this combination. Let's see, will it let me do that? Yeah. Okay, so let me read it to you one more time and then I'll go in there. So we have 5 kids. Probability that 2 of them have type O blood, and the probability is 0.1. So I guess we need to check first, is this binomial? So let's check bins. They either have type O blood or they don't. So that works. Each trial is independent. The blood type of each kid depends on their parents, but is not affected by the kid that was born before or after them. So yes, these trials are independent. Is there a fixed number of trials? Yes, there were 5 kids. And is the probability of success the same? Yes, each child has a probability of 0.1. So I can use that binomial formula to find the probability. So I'm going to do the probability that X, our random variable, is equal to 2. We want to know the probability that 2 of the 5 kids have type O blood. That is then equal to 5, choose 2, times the probability of success, which was 0.1, to the, let's see, how do I do to the power? There we go. To the second power, times 1 minus the probability of success, 0.9. Oops, sorry, 0.1. 1 minus 0.1 is 0.9 to the 5 minus 2 power, which is to the third power. So this is, how do I do an approximately sign on here? This is approximately, and then in my calculator, here's what I would do. I would go to second vars, and then letter A is the binomial PDF. I'll show you CDF here in just a little bit, but the binomial PDF is the binomial probability distribution function, but I think of the P as one particular value. P for one particular value. So I go to binomial PDF, my number of trials is 5. My probability is 0.1, and my X value is 2. We said that over here, probability that X is 2. And then I can hit enter. And if you guys type it in, if you have the older version of the calculator, then it just has parentheses and you type it in as your N, P, X, just like that. Then we can hit enter, and I get 0.0729. So I guess I didn't need an approximately sign because that was exact. Let's see, can I go back over here and say equals? Now I accidentally erased it off my calculator screen, so let me find it again. Okay, so 0.0729. Or if you wanted to say approximately 0.073, that would be fine. Okay, now let me move this down here so you can read it. All right, so again, you have to show this work to get credit. You have to show this work. Then you can punch it into your calculator. So in the calculator we did binomial PDF of 5, 0.1, 2. Okay. All right, let's try another one. For number 4, if 27% of all adults in the U.S. are college graduates, find the probability that 3 out of an SRS of 4 adults in the U.S. are all college graduates. So is this binomial? Yes, they are either a college graduate or they're not. The trials are independent. We're taking an SRS of 4 people out of all adults in the U.S., so definitely we can consider those trials independent. Probability of success is the same. It's 0.27. And is there a fixed number of trials? Yes, we're taking an SRS of 4 adults. So let's go into my equation editor again here so I can type this. We are finding the probability that x equals 3, which is 4 choose 3 times the probability of success, which is 0.27, to the 3rd power times the complement of that. You can type the 1 minus, or you can write the 1 minus 0.27, or you can just go ahead and write the 0.73 to the, and then again, you can write the 4 minus 3 power, or you can just write to the 1st power. But you still have to at least show this much work, at least this much work. Then you can go to your calculator. This time I need my binomial PDF. I'm going to cheat and do my second enter and then edit this. We had 4 college grads. Probability of success is 0.27, comma, and then the number of successes was 3. 3 out of 4 are all college graduates. Okay, so our probability is 0.057 about. Let's see, approximately 0.057. Okay. Again, you have to show all of this work for credit. You have to show your work. All right, now before I go on to the next one, I want to show you what that binomial CDF in your calculator does. So this is probably letter A or letter B, but it just depends on your calculator. It is also obviously in second vars, and you're still putting these in the same order, NPX. But here's what this does. The binomial CDF is the binomial cumulative distribution function. So it's going to give you everything less than or equal to a specified value of x. So if you say x is 2, it's going to give you 0, 1, and 2 all combined, all cumulative. Obviously, we can't have a negative number of trials, so it's only going to start at 0. But this is cumulative, so it includes the value that you type in for x and everything less than that. So it's everything less than or equal to a specified value of x. So I will always go back and write my probability that way, even if it's a greater than or a less than or just a less than. I will rewrite everything as less than or equal to, and I'll show you that here coming up. So let's look at number 4, part B. Same situation with probability of college graduates from all the adults in the U.S. And again, we have 4 in our sample, and the probability of success is 0.27, okay? So if we want to look at the probability that 2 or fewer of our sample of 4 are college graduates, then here's what I would be looking at. We are looking for the probability that x is less than or equal to 2. 2 or fewer are college grads. That is then, what do I have to do to find this? Because I need probability that x is less than or equal to 2. I'm going to need x equals 2. I'm going to need x equals 1. And I'm going to need x equals 0. So I need to show my work for all 3 of those. I need to find the probability of x being 0 out of the 4. So I need my choose. Oops, I guess I have 2 sets of parentheses there. Okay, let me go back. I need 4 choose 0 times the probability of success, which was 0.27 to the 0 power, times 1 minus that is 0.73 to the 4th power, 4 minus 0. Then that's going to be plus another choose, 4 choose 1 times my 0.27 to the 1st power times my 0.73 to the 3rd power, 4 minus 1, plus one more, my 4 choose 2 times 0.27 to the 2nd power times 0.73 to the 2nd power, 4 minus 2, which comes out to be, then I can go to my calculator. So this time I'm going to go into my second vars and pick my binomial CDF. I have 4 trials. Probability of success is 0.27. And my x value is going to be 2, which means I'm including 0, 1, and 2 because I picked binomial PDF. Oops. I meant to pick binomial CDF, and I clicked on the wrong one. Let me try that again. Binomial CDF, there we go, of 4 trials, probability 0.27, x value of 2. Yeah, now it says binomial CDF, which comes out to be 0.937 about. Oops, I'm trying to type in the wrong thing. 0.937. There's a lot of typing there. Okay, there we go. All right. Now for part C, what about, is this the same as the probability that less than 2 are college graduates? Less than 2. Is that the same thing? No, it is not going to be the same thing. I'm going to copy and paste this because if we are saying just less than 2, then it doesn't include the value 2. So I'm going to change this to strictly less than 2. And so I want my 0 and I want 1, but I do not include the probability of 2. Oh, can I not edit that? Something froze on me here. Let me see. Can I go back like this? Okay, I thought I could edit that. I am not including the value 2 because it is strictly less than 2. So I'm just including 0 and 1. So now I need to go back to my calculator and do my binomial CDF, which is still 4 and is still 0.27, but what's my last number? Because the probability of being less than 2 is actually equal to the probability that x is less than or equal to 1. I don't know why it didn't put the other parenthesis. There we go. So see how I changed my notation from just x is less than 2 to the probability that x is less than or equal to 1. So in my calculator, I need to change that last value to a 1 because I just want to include 0 and 1. So now if I hit enter, I get 0.704 about. Now I've updated my equation there. So probability that x is strictly less than 2 is the same thing as the probability that x is less than or equal to 1. This is discrete, right? So there's no 1.5. There's just 0, 1, 2 that could be college graduates. So it's the probability that I get 0 or 1 is 0.704. And you have to show your work. Have to show your work to get credit. All right. So last one, what about this? For D, what is the probability that of 3 or more college graduates in our sample of 4? What is the probability of 3 or more? So let me steal my notation. We are doing then the probability that x is 3 or more, which is greater than or equal to, greater than or equal to 3, which is the same thing as the probability that x is, again, I always like to put this in less than or equal to notation, less than or equal to, if I do 1 minus the probability that x is less than or equal to 2, then that would give me the probability that x is greater than or equal to 3. So I want 3 or 4, right? X is greater than or equal to 3. So I'm going to instead do the complement and get rid of, do 1 minus the probability that x is less than or equal to 2, because that would get rid of 0, 1, and 2 and give me the probability that x is 3 or 4. So this time, I don't actually have to show all of this work. If it will let me delete that. Because we found the probability that x is less than or equal to 2 in part B, wasn't it? Yeah, part B. Okay, equation editor, catch up with me. If I go to the calculator and then come back. Nope, it's just really mad at me. Shoot. Okay, well. Can I escape out of there? No. Okay, let's see. Can I write with pen? No. Oh, man. Okay, well, let me find the answer in my calculator, and then we may just have to... Oh, there. Okay. Let's see. Maybe it will let me go from here. Yeah. Okay, because we found the probability that x was less than or equal to 2 in part B on the same problem, then I don't have to show all of my setup because I already showed the work for less than or equal to 2 on part B. I can just say this is 1 minus, what did we have for part B? 0.937. So 1 minus the 0.937 is 0.063. Oh, I keep typing in the wrong thing. 0.063. That is all I need to show for my work on this one, just because we did this probability in part B. Okay? All right, that is it for day 1 of 8.1 binomial distributions. We will finish up 8.1 on Monday, and then we'll move on to 8.2 Tuesday and block day, and then I think I've got review Friday and the following Monday, and then our chapter 7 and 8 test on Tuesday. But I guess I can check PowerSchool to be sure about that. Let's see. Class pages. I know I need to update homework on here a little bit, but let's see. December. Yes, our chapter 7 and 8 test will be on December 11th. And then we review for the final. And then I think I need to update this too, because we may actually start our final on the 18th and then review on the 19th and then finish our final on the 20th. Because the classes on the 19th are short, except for first hour, because the final is that day during first hour. So, yeah, we're probably going to start our final on the 18th and then have another day of review on the 19th and then take the rest of our final on the 20th. But we can talk more about that when I am back. I hope you guys have a fantastic weekend. Okay, I totally got ahead of myself and I forgot there was a question 5. Okay, let's do question 5 real quick. The median annual household income in the U.S. is about $59,039. Among 5 randomly selected households, find the probability that 4 or more have incomes below $59,039 per year. So we are finding the probability that 4 or more have incomes below $59,039 per year. So let me go back to here. We want the probability that X is greater than or equal to 4 or more, which is the same thing as 1 minus the probability that X is less than or equal to 3. Right? Because if I want 4 or 5, then I am doing 1 minus the probability that X is less than or equal to 3. That would get rid of 0, 1, 2, and 3. Okay, so let's update our equation here. We need 5, choose 0. And the probability of being below the median is what? Yeah, 0.50, because the median is by definition halfway, right? So half of the people have incomes above and half below. So 0.5 to the 0 power times 0.5 to the 4th power, or to the 5th power, plus 5 choose 1. Oh, this all should be 1 minus this, shouldn't it? Oops. 1 minus. Okay, there we go. Probability 5 choose 1, 0.5 to the 1st, 0.5 to the 4th, plus 5 choose, well, here, let's do this, plus, let's use an ellipsis, plus, and go to the last one, 5 choose 3, times that 0.5 to the 3rd times 0.5 to the 1st, no, to the 2nd, because it would be 5 minus 3, which gives us, oops, approximately, okay, let's see on the calculator. So we're doing 1 minus, second vars, our binomial CDF, cumulative distribution function, with 5 trials. Probability is 0.5. X value is 3, because I'm getting rid of 0, 1, 2, 3. I want 4 or more. And enter, enter. I get 0.1875. So I guess I can make this an equals to sign. Equals 0.1875. That one is off the screen because it is so big. Oh, geez. Let's make that smaller so it all fits on the screen. Okay, there we go. All right, that really was the last problem. So tonight's homework is page 516, numbers 1, 3, 5, 6, 8, 10, 11, 12, 14, 16, and 18. Page 516, 1, 3, 5, 6, 8, 10, 11, 12, 14, 16, and 18. Okay, now really have a fabulous weekend, guys. I will see you on Monday.